All right, and I kind of previewed this at the end of the last video, but remember that every definite integral represents an area underneath a curve, right? And so the only question is, we learned about use substitution. How does that impact the area? And so um, let's maybe look at that in this example, okay? So our question is, which of the areas are equal, okay? They aren't nice geometrical shapes, so I can't say just from eyeballing them if they're going to be the same or not. I mean, they look kind of different. Let's see what happens, okay? Um, so let's look at this area first here. Let's call this A, okay? So if I look at A, this is going to be equal to, let's see, if I set up the integral, it'd be, okay, x bounds 0 to 1, and it would be the area underneath e to the square root of x dx. Okay. How would I integrate that? How would I find that? I actually have no clue because I can't do it without u substitution. So let's try a u sub. Let's do, okay, I like u as the exponent on e, right? So let's try square root of x. Okay, but that might make things a little bit messier. What if I did, let's see. Actually, it might make things messier, but again, I'm trying to substitute in for dx. If I square this substitution, I would get, u squared equals x. And then if I differentiate that, I'd get 2u du is equal to dx. So this would be actually, let's see, I'd have to change the bounds here in a moment. Integrand would change to e to the u, right? Okay, and then dx is 2u du. And then bounds, okay, put in 0. Square root of 0 is 0. Square root of 1 is 1. Okay. Oh, okay. That's interesting. And then I could go on and integrate it, right? I'm going to come back and do the integration if I can. That one, actually, I don't think you can integrate that till next week, but we're going to leave it like that. B. Let's look at B. So if I find area B, right, that's still integral from 0 to 1 underneath the function 2x e to the x dx. Oh, wait. Isn't that literally the same thing, just with a different variable, right? So e to the u, e to the x, 2u, 2x, dx, or du, dx, and 0 to 1. So these are actually the same. So A and B are the same, even though they look really different, right? So when you do a u substitution, the geometry changes a little bit because you are changing the function, you're changing the slope of that curve or how that curve moves through space. Next, our last one, I'll do this in red, so this is C. Okay, let's see what this is going to be. So this is going to be 0 to pi over 2 e to the sine x times sine 2x dx. Okay, well, you're probably thinking that u is going to be, if we do u sub, that's going to be sine x, right? So that's a very good guess and actually ends up being correct. So I would do u is equal to sine x, and then that means that du is equal to cosine x dx. But I have sine 2x. Oh, wait, there's a trig identity, right? 0 to pi e to the sine x times 2 sine x cosine x dx. Okay, and now I can do the substitution. Okay, 0 to pi over 2, that should be integral. Come back and do the bounds. E to the u times 2 sine is u, and then cosine x dx is du. Okay, this better be from 0 to 1. Put 0 in, sine of 0 is 0. Yep, sine of pi over 2 is 1. Yes, indeed. So all three of these areas end up being the same. You wouldn't know it without doing the or without going through the use substitution. So use substitution can make areas that are seemingly different the same. Yay! That's the punchline. There we go. So in this video series, we learned about how to do use substitution. Again, technically in this process and all the examples, I did not, and shame on me, for going through and verifying that we have continuous and differentiable functions, but all the functions we were working with were nice differentiable functions. So we got, you know, I guess everything that we did was valid as a result, right? So we just had to work on maybe some specific domains that we didn't identify. So square roots, you know, we had to do 0 to infinity. But otherwise we worked with polynomials and trig functions. Tangent, so you just have to ignore like the different multiples of pi over 2. Otherwise, assuming you're within the domain, we're fine. All right. So that's one thing that you should always verify. I didn't. Oops. But otherwise, we now have another technique of integration to use.